Hi everyone, this is the video about the decoders used in digital systems, and throughout the lecture I will show you how do we use Verilog in describing decoders. First, let's look at the basic decoders, which is binary decoders. The diagram shows the general decoder structure, where normally in binary decoder we will find a set of input ports representing or receiving the binary number or binary code, and there is a small number of enable ports to enable the decoder. At the output side, normally it is more ports compared to the input ports, and the output generated normally correspond to the binary number received or binary code received at the input side. For example, if you have 2 to 4 decoder, then the output generated is corresponding to the 2-bit binary given at the input side. Let's look at the detail of the binary 2 to 4 decoder. So we have the 2-bit at the input side, as the name tells. 2 refer to the 2-bit of the binary input, and 4 here refer to the 4 bits output to be generated corresponding to the 2-bit binary received at the input side. And it has only one enable port to enable the decoder. So this function table shows the output of the decoder given based on the binary number received at the input side. So when the enable is activated or when the decoder is enabled, so the output generated here is corresponding to the binary number. For instance, this row show the binary number received is 00, then the output that has index 00 will be turned on, whereas the remaining output will be off. Okay? When the input is binary number 01, then the output holding the index 1 will be turned on, whereas the remaining will be 0, and so on. So in digital electronic circuit, which is the basic course you've learned for digital design, you have learned how to transform the function table of the 2 to 4 decoder using the knowledge or technique of truth table and K-map to get the schematic of the 2 to 4 decoder. And this diagram shows how the circuit look like for 2 to 4 decoder. In Verilog, you can describe the 2 to 4 decoder using either the procedural block as shown in the left side here, or you can use the continuous assign statement with the support of the conditional operator. So let's look at the first example, the first type of coding that use the always block or the procedural block. So first we have the header of module followed by the module name, and in the bracket the list of the input and output. So in this case we use a vector way to declare the input I. So we don't need to put I0, I1, just put I that represent the 2-bit I here, and just put Y that represent the 4-bit Y at the output and the enable pin. So since the I consists of multiple bits, you can use the vector form or method to declare I, and where you can put in the square bracket 1 column 0, which means I consists of bit 1 down to until bit 0. And input also have enable port and also followed by the output, which consists of 4 bits. Okay. And you have the type rec here because you are using procedural block, and the output y is also the signal that will be produced by this procedural block, where you notice that the y is also the left hand side variable under the procedural block. So in this case, the ruling of the data type of the Verilog require us to declare y as type rec. Okay, so after the always alias construct here, then in the sensitivity list you put the signal that will determine the output of the decoder. So from the diagram here you can see that the signal that determine the output y here will be I and enable. That's why you can put here enable or I, or you can use the later way where you just use comma instead of or. Enable comma I. Okay, so under this always block, because it has two statements, so you need to enclose the statements with begin and end here. Okay, begin and end here, the end here. Okay, so um so first you put y equal to 0, because actually it is to show that you want to assign the default value 0 to y. Okay, then after that, if enable signal is on. Okay, so when you use case statement to describe decoder, so one good thing is you will see that you just need to code based on the function table of the decoder. Okay, so put y equal to 0 as a default value, then if enable equal to 1, that will represent the following row of the function table for decoder. So if enable equal to 1, then you put a case statement to list down all the possible value of I, which is from 0, 0 until 1. Okay, so case followed by bracket the conditional variable from 0, 0, 0 until 1, 1. You can put it in binary format B or in hexa format like shown here. Okay, so when I equal to hexa 0 or 0, 0, then y will be equal to, look at the function table of this row, then when I equal to 0, 0, y will be equal to 1. So y will be equal to 4-bit 1. Okay, when I equal to 1, then y will be equal to 2 as shown here, and so on. So after you list down all the possible values of the I signal and the statement that show what happened if I holding that value, then you can end the case statement with end case. Okay, since you have a begin after the if, then you have to end it with end also. Actually, in this case, you don't need to have this pair of begin and I mean not necessary to have this pair of begin end, because under the if there is only one statement. So having the begin end is nothing wrong, okay, but you can also remove it since only one statement, and you don't need to enclose the statement with begin end. Okay, so this is one way, and then the second coding show how they are it is described using the continuous assign statement with the conditional operator. Conditional operator consists of question mark followed by column. Okay, where you will first put the condition for the before the question mark, and if the and then followed by the true statement when the condition is true, and followed by column, and followed by false statement, which means what happened when the condition is false. Okay, so this is a very compact coding. As you can see here, we can just use the shift operation to describe the decoder. Okay, so here the assign statement here means y equal to y depend on the enable signal. If enable signal is 0, which is disabled, then the y will be 0 corresponding to the first row here. But if enable is 1, then the y will receive the signal that is in the shifted pattern. Okay, so now let's do some revision on the left shift operator here. So if we have one left shift 1, that means this number 1, okay, when written in 4-bit, okay, it will be 0001. This number 1 will be shifted to the left for 1-bit position. So the resulting pattern will be 0010, yeah, which means this bit with this value 1 has been shifted to the left for 1-bit. Okay, so that is the resulting bit pattern after the shift left or left shift operation. Okay, so when you have this shift operation written with the variable, that means it depends on the variable I, how the shifted pattern will be generated. So if it is I equal to 2, then the bit 1 will be shifted to the left for 2 position as shown here. So if I equal to 3, then it will be shifted 3 bits. So at the end, this one single operation of uh, left shift written in the form of variable I will give you will represent the function table shown here. So when I equal to 0, so it will stay as 1, the original 1. When I equal to 1, it will be generated as 0010. When I equal to 2, and as shown here, and so on. So this highlighted shift left operator will is representing the shifted pattern of this output, which is also the truth table or the output you can see in the function table of the uh, decoder. Okay, that's why you can use just one line to describe the function table of the decoder, 2 to 4 decoder. So you may need to design 3 to 8 decoder. Okay, and if you recall, you have seen this 74138, which is the name of the number of the chips that function as 3 to 8 decoder. And then you find like maybe if you remember, they have 3 enable input ports and 3 input that represent the 3-bit binary, and the output here could be active low, could like this, or it could be active high. Okay, okay, so this is fixed by the designer of the chip 74138. But when you design it using the Verilog code, it's up to you whether how many enable pin you want to design for your decoder, 3 to 8 decoder. Yeah, so in for the chip 74138, there's some reason why they need so many enable ports, because they are useful when you want to use multiple units of 74138 chips to build a bigger decoder. Okay, beside the binary decoder, you may find other special decoders such as the 7-segment decoder. So 7-segment decoder is the circuit that also receives the some coding, which can be a binary number. Okay, and then it produces the outputs that are corresponding to the binary number, but this one it is not the binary decoder. Okay, so the output generated corresponding to the binary number received, but also need to be suited to the usage of the system connecting to it. So in this case, the system connecting to it is the device connecting to it is a 7-segment. So the output, the 7-bit output here will represent the on and off of the segments on the 7-segment display, and the character to be displayed here will be corresponding to the binary number received. So if it is receiving 0000 as a binary number at the input side, then it will display a 0, where the output should only activating segment A, B, C, D, E, F. Okay. So if it receives 0001, then the output here should only turn on B and C. So in other words, A should be in the logic low, logic 0. Only B and C should be at logic high to turn on the segment B and C. Okay, so how it works here, I don't show the detail of the circuit, but basically it's just like the pin, each output pin, like A connect to a segment in the 7-segment display. Like A connect to A, and then the other end of the segment will go down to the ground. So in this case, A need to be at logic 1 in order to turn on the segment. Okay. So the segment could be made of the LED, for example. So this is under the structure or connection, what we call the common cathode, where all the 7 segments connecting to the common node, which is a ground. That's why we call it common cathode. Okay, so for common cathode 7-segment display, to turn on you need a logic 1. Okay, you may okay, so you may find the common anode type of the 7-segment display. But now let's stick to the how do we use Verilog to describe our 7-segment decoder to display 0 until 9 for the usage of BCD numbering display. Okay, of course you can design to display 0 until 9 and then followed by A, B, C, D, E, F for all the 16 characters. Yeah, so it depends on the specification of the design given to you. So in this example, you just need to decode 0 until 9. Okay, so one way to describe using the Verilog is as shown here. Okay, so as you can see, the input output declaration can be also done in the later version of Verilog, where you can declare input and output right away in the bracket after the module name. Okay, so in this example, I use again procedural block. Okay, and the condition. Okay, and you can see here the output is of type rect for A, B, C, D, E, F, G, because the A, B, C, D, E, F, G are generated by this always block, which you can find they are at the left hand side of the equal sign. Okay, so I can use case statement because as I explained in the previous example, if you have a complete truth table or function table like this, so one straightforward way to code them in Verilog is use the case statement, where under the case you just put in the bracket the signal that will determine the output of the 7-segment display, 7-segment decoder. So in this case, the signal involved is ABCD. So I put here ABCD, but I have to use the concatenation operator where you can see the curly braces. Then inside here I put ABCD separated by the commas, because in case in the bracket you can only put one signal. So but I have 4 signals to be put, so I have to concatenate them into a signal, into a group of signal. Then only I can put in the case statement bracket. Okay, and then if ABCD equal to 0, corresponding to this row, ABCD equal to 0, then my decoder output will be 11110, will be 7-bit 1110, and so on. You code in this way, and it's a good practice to put default at the last row of the case statement to show that if the value of A, B, C, D is not listed here. For example, we only list 0 until 9. But what about 10, 11 until 15? So that is not listed. Then the compilation will refer to the default line here, okay, to generate the corresponding circuit or logic. Okay, so if it is out of range 10 until 15, then we don't care about the A, B, C, D, EFG output, and you can make it the default value, which is 0000, which means you turn off all the display. Okay, so I forgot to explain the asterisk for the combinational logic. When you use the always block, actually you can put the asterisk here instead of listing all the signals like ABCD, capital ABCD here. Okay, for combinational logic. Yeah. Okay, so as I mentioned just now, the version of the 7-segment display plays a very important role for you to decide how to design the 7-segment decoder. If you are using common anode 7-segment display here where all the segments are tied to VCC, then to turn on a segment, say segment A, then your 7-segment decoder need to produce 0 instead of logic 1. Okay, so it will be reverse of the common cathode 7-segment display. So please take an important note where you need to find out what kind of 7-segment display you will be working with before you design your own 7-segment decoder to connect to this display. So other special decoders could be it is still a 7-segment decoder, but a special one where instead of displaying the number, probably some application require you to design the decoder that will ask the display to display certain character like hello. Okay, when 000, then H should be displayed. 1001 is given at the input, then E should be displayed, and so on. For 100 until the end, it should be blank. That means you need to produce some the logic 0, all 0 or all 1 here to turn off the segments. 0 or 1 depend on, as mentioned, is common cathode or common anode. Okay, so special decoder could be as another one shown here below. The application just want you to display Y, capital Y, ES, or small letter N, or which can display yes or no in the some application or digital system. Okay, so whatever special decoders you are required to design, the most important step for you is first you need to complete the truth table. Okay, so how to know what truth table, what columns you need to have in the truth table? So refer to the input and output of the decoder. So your input consists of C2, 1, and 0. Then list it at the input column and output column A until G. And then fill up the input at the binary ordering and the output based on the segments to be lit up corresponding to the characters in the specification. Okay, so this is very important. If this is done and it is correctly done, then you can just move to the Verilog coding step where you can use a case statement to code the design. Other special decoder could be the decoder that link or work with the dice display. Like here, there's a dice display here where when 000 at the input, sorry, should be C1, C2, C1, C0. Okay, so input C2, C1, C0, 0, 0, 0, then the dice blank. If 0, 0, 1, then there's only the middle, the center dot lit up. Okay, when 0, 1, 0 representing 2, only dot A and dot F turn on. Okay, so it could be this way. So you can have the function table, and more importantly, you complete the truth table before you move to the Verilog coding using case statement. Okay, you may also need to ask to design the matrix dot decoder, which it depends on how many dots you have on the display. So the decoder design will be different. Okay, so if you have many dots like this, probably you need a one row decoder and one column decoder. Okay, so that is about the basic knowledge and on the decoders and how to design them in Verilog. I hope this video is useful and can help you to understand about decoder. Thank you.